Hey class, how's it going? My name is Luis Orozco. This is Stephanie Hernandez, my partner. Our company name is Zeus Processors, and our feature processor that we're going to present today is called the Poseidon.
So for today's agenda, we're actually going to talk about where the name of our company and processor comes from. We're going to talk about the MIPS processor, the baseline processor, what went wrong, debugging methods, interrupts, and the future enhancements we plan to make, and then any final questions. So feel free to ask questions throughout the presentation.
So why did we choose the name Zeus Processors for a company name?
So both Luis and I are really into Greek mythology, and Zeus is actually the king of all of the gods, so we took it as representation as the top processors of all of the processors.
And why did we choose Poseidon as our processor?
So Poseidon is actually also a Greek god, and he's the god of the sea, and he's actually able to cause earthquakes, so in our case it's going to cause fear to all the other processors.
Okay, so our MIPS processor is a reduced instruction set computer, so it actually follows a Harvard architecture. It does do a big Indian architecture, so what that means is that the most significant byte gets stored into the lowest bit of memory, and the least significant byte gets stored into the highest memory location.
So this is the overall architecture of our processor, and we're going to look into detail of each of them. So first we're going to talk about the integer data path.
So what the integer data path does, it instantiates our register file, which we will go more in depth while this presentation goes on. And it also instantiates the AOU. And AOU we need to implement these two registers called the high and low registers. We use these two registers for division and multiplication. We need to store when we do multiplication, the product turns out to be 64 bits, so we have to split the product into two, and we have 32 bits here, 32 bits here. And for division, our quotient and our remainder has to be stored individually into the high and low.
Our demugs is used to actually select which one of the registers we're going to write to. So if we use T address, that's usually used for an I type instruction or for a J type instruction. Our D address is actually used for an R type instruction, so add, subtract. Register 31 is for our return address, and register 29 is used as a start pointer, usually for interrupts.
Okay, so our register creates it generates 32. Our register file is a two-dimensional array which generates 32 registers, which each register is 32 bits wide. We do have a register 0. The register 0 we cannot write to. We use it for most common use would be to, for example, we don't have a move instruction in our MIPS processor, so we would use the add instruction in order to transfer the register to another register.
Next, we're going to talk about the LAU. The LAU stands for Arithmetic Logic Unit, and it actually instantiates the multiplication, division, and MIPS modules. And using an assign statement, we actually select which one of those we're going to choose. Multiplication, division, or MIPS. And the MIPS module actually is what includes all of the baseline instructions, so it has the logic for add, subtract, and all of the baseline instructions. Next, we're going to talk about data memory.
Okay, the data memory module allows us to read or write. We use this for loads and stores, and we need this module is actually when we write is clock dependent, so it's synchronous, and when we read it's asynchronous, it's not depending on the clock.
So here are the selects for our data memory. So in order to write to data memory, so for instance in a store, we actually have to assert our data memory chip select and our data memory write select. Or if we're going to read to memory, then we have to assert the data memory chip select and the data memory read select. And next we're going to talk about the CPU-IU, or the instruction unit. So the instruction unit is actually what instantiates the program counter, instruction register, and the instruction memory. So instead of actually having hard-coded values for our S address, T address, and our D address, which are our sources and destination registers, we're actually going to use the instruction memory, so usually using a DAT file or whatever we make to test it. Then the sign extension is usually used for I types, so since it's a 16-bit immediate value and we have to make it 32, we use the sign extension here. And then DN is hard-coded to 0 since in our processor we're actually not going to write to the instruction memory. And our PC mux is actually the mux that tells us what's actually going to go into the program counter. So you can either select just PCN or the address of a jump or the address of a branch instruction. And then the I/O memory is actually another instantiation of the data memory, and here's where we set the interrupt signal for our interrupts at a specific time, and it's used for input-output enhancement instructions. So now the MIPS control unit.
The MIPS control unit creates a control word for all the instructions. So for example, when we need to do the state reset, fetch, decode, and of course XP states depends on the instruction, what instruction we're doing. In this case, our example is shift right logical, and this is just represents our Verilog representation of our control word for the shift right logical.
And we use the RTL to determine which signals are going to be asserted and which ones are going to be deasserted. So what went wrong? So our jump and link and our interrupts actually went wrong, and we're going to talk about why. So at first, we were just getting results that said illegal instruction fetched. So that was a pretty big headache for a couple of weeks. And then when we finally hit the big instruction, we're like, yay, it finally works. However, we realized that it was actually not hitting the break we wanted. It was actually going straight from jump and link, and instead of jumping to our load word instruction, it was actually continuing on to the next instruction, which is a Louis OID, and it was hitting this break. However, it was supposed to jump here, perform this loop using the branch not equal instruction, and then jump register, and then this break. So we realized that a little too late, but we still went on and figured out what the problem was. And we realized it was a problem because register 13 is actually being compared to 0, and then when our final results, register 13 is not 0, then obviously there's a problem. So thanks to our professor, we actually learned a lot of debugging methods. So first we started off by displaying specific registers. So as this example, we used $display to display register 5. Then we started printing out the values of our program counter and our instruction register at specific states. Then after that, we actually started outputting our program counter instruction register everywhere. So after the fetch instruction, decode, even after the case statement, just so I can see where the problem was going. Then when that also didn't help us, we started displaying, we actually printed out, we took our professor's advice and we printed out all of our block diagrams and actually labeled every single wire, and we started outputting every single wire to see where the problem was going. And here's actually an example of everything when we started debugging, of everything we started outputting. Another way we debugged was using the waveform. So we actually input different states, or our state block here in our waveform, or different things we wanted to see, signals we wanted to see in our waveform. So for instance, here we actually put in our state in our waveform. So for instance, depending on what values we put in our parameters, so 1 was fetch, 2 was decode, and say 17 was add, for instance, we were actually able to see what happens at every specific state. So it actually gave us a clearer picture of what was going on and where a problem could be located.
Okay, so after struggling and staring at our code for so long, we decided to take a vacation to Fiji. And once we came back, we realized that we'd forgotten how to count, because our problem was right here. I don't know if you guys can spot, but there is only 7 bits here, and it was supposed to be 8 bits. And that's what would happen. That was our problem. We miscounted, and that's what was happening.
So your PC select was always 0.
Exactly. So it was actually, just getting 0 and then the one PC low, and it was incrementing the counter. But we didn't realize that, I don't know, it was just 3 weeks of headaches instead of headaches.
How long did it take you to find that after we talked?
About a week and a half.
So after you learned to print out all the wires and...
Exactly.
Yeah.
So then I realized something was going on, something was missing, because for some reason, my PC select was always being 0. So I was like, why is it being 0? And I tested other instructions. I'm like, wait, my PC select does change values, so there's nothing wrong with PC select. Something's wrong there. So we debugged, printed out everything, and we came to the conclusion that we miscounted. So the right way, and I actually didn't realize that until I actually decided to split up my instruction memory signals from my PC and IR, and that's when I realized, wait, my numbers don't add up. Once I fixed this, so now it's actually 5 bits on top and 3 bits in the bottom, a total of 8. And then I ran it, and that's when it actually worked completely. And then we're gonna go set up. So So here you can see how it's actually 5 bits, 3 bits. And we were able to know that it was actually working properly because now our register 13 was actually 0, and we actually calculated our results correctly to make sure we get the right ones.
Okay, so interrupts. I'll go briefly on what it is. So an interrupt requires an interrupt acknowledge flag to be set. The processor finds out that there's an interrupt flag set, then we go to the ISR, which is the interrupt service routine. Before going to the interrupt service routine, we have to push our flags into the vector. That way we can save the present state of the flags, and when we come back from our ISR, we can continue using those flags. That's where we're going.
So for future enhancements, we're planning to make a barrel shifter and pipeline. However, since we didn't have a lot of time, we're actually still in the process of completing our barrel shifter, but we did get started on that.
So we did get started on the barrel shifter. What we did is we had a five parameters, one of them being our input, the other one being our output. SHAP stands for shift amount, that's how many times you want to shift to the right, to the left. And function select is what decides if we're going to shift left or right, or in this case, rotate left. And shift enable, it has to be on in order to use our barrel shifter. This right here is an implementation of our shift to left. And for it to work, we did a case statement. The case statement is sensitive to SHAP, which is shift amount. So if you want to shift twice to the left, for example, this section of the code will be executed. And the input just gets shifted twice to the left and gets saved into the output. Our shifting right is very similar. The only difference is that obviously you just shift right. Okay, and for our shift left, it was a little bit different. On this one, we actually had to do a concatenation in order for it to work. So for example, right here, we had to concatenate the bits being shifted, which was the most significant bits, and throw them on the back. The other ones, we had to throw them in the front, and that's how we implemented the shifting left. For rotate left, I actually have a visual example of how we did it. So back to basics, rotate left, this is a little figure of what happens. The most significant bit gets passed all the way to the least significant bit, and then all the other values just get shifted.
That's if we're rotating left by 1.
Does MIPS have a rotate left? Do they have a rotate right?
No.
But you were going to do a rotate.
Yeah, in the barrel shifter.
Okay. Enhanced instruction.
Yeah. Nice. Keep on going. Okay, for our shift right arithmetic, this one got a little bit tricky because for shift right, we do have to accommodate for the most significant bit. When you're shifting right, the most significant, instead of shifting in zeros, you're actually shifting in whatever the most significant bit is. So the way we did that in code, we actually had to sign extend the most significant bit according to how many bits we're going to shift.
Right.
So for example, we're going to shift twice. Right here, we had to concatenate it to 2. To 2. That way, this signifies a signed extension, and then we concatenate it to the overall result, and we throw it back into our output value.
So thank you for listening. Do you guys have any final questions on anything?
Yeah. Why did you do a rotate left? Why left?
Enhanced instruction. We didn't get to do right. We wanted to do both actually,
Okay.
but we just got to rotate left. So it's still in the process, not complete, still in the process of making, but for now we have to rotate left as one of our enhanced instructions. I mean, rotate right would have been the same thing, just right.
Right.
So to be clear, you did do those instructions, or you didn't do them?
Yeah, we did the instructions. We're just still in the process of debugging. So it wasn't on time when we turned in our project.
Okay, so you didn't have any implementation,
Yeah.
Not
verification.
Not when we turned it in.
Okay.
But we went ahead and continued the project
Mhm.
even after we turned it in,
Mhm.
just to see what we could be able to do.
Good.
We still yet have to implement it to the data path in order for it to fully work. And yeah, so if I implemented it to the data path and then
What would it take to just take that unit as a separate module and implement it with what's currently in your quote ALU?
So from our, take a look back.
go back to the data path.
Well, it's like being on a roller coaster.
There you go. Okay, for this one, my thoughts, my initial thoughts so we can implement it in here. I was going to throw it into the ALU initially, but I don't know why it was a bit confusing for me. So the way I was trying to do it was grab it actually from the T, our T being our input
Uh-huh.
to the register file, and it was the guy was just gonna be hanging here. And then we didn't get too far with like thinking through like how exactly we're gonna implement it, but I know for sure that it was gonna get kind of iffy if we throw it into the ALU. So
It'll go directly to LU out. So it'll go from T to the barrel shifter and on to LU out if we choose to use the barrel shifter. If not, our T signal would just go straight to the LU. So if we wanted to do a barrel shifter, it would know through the enable to go through here instead of go through here.
then we would have to add a mux.
To
Yeah,
select
yeah.
whether it goes from LU.
So we all know in the ALU, that your blue module, there's actually multiple sources that come out.
Mm-hmm.
So that means there's three. I think there's the multiplier, there's the divider, and there's the integer.
Right.
Yeah,
So you would just add it as a fourth thing.
exactly.
So you wouldn't have to bring it out anywhere. It's the same principle. And then you'd need the mux, which is already there. There's a 3-to-1 mux kind of.
So just make it
You just make a 4-to-1.
so you were right.
The inclination was there. That's how I did it.
Okay.
Alright.
I think that way everything's still right there in that one module. It just extends the capabilities.
Yeah,
so
we
you
did
was right.
still have to implement it, but that was our initial.
So now we know
Yeah, yeah,
it's
yeah.
to get it.
Any other questions?
There's tamales in the back if you just want to get some. I just forgot plates for some reason. So we'll go get napkins or something.
Okay.
And they're homemade too. So.
Oh, that's so good.
What they're probably called? They're chicken.
Okay, thank you very much. That was good.